The water coming out of your kitchen sink right now is not waste. The water draining from your shower, your laundry, your vegetable washing basin, none of it is waste. It is water you already paid for, water you already hauled or pumped or collected, water your garden desperately needs. And you are burying it in a pipe and sending it away forever because someone decided decades ago that all used water is dirty water, and dirty water goes underground, and that is simply the way things are. It is not the way things have to be. There is a category of water that engineers call greywater. Not black water, not sewage, not toilet waste, not the biological hazard material that genuinely requires serious treatment before it touches anything you care about. Greywater is the water from your sinks, your shower, your bath, your laundry. It contains soap residue, skin cells, food particles, trace nutrients, and a microbial community that is, in most cases, dramatically less dangerous than the soil in your garden already is. And in a survival context, in an off-grid context, in a world where every litre of water represents effort and energy, and sometimes genuine scarcity, sending greywater into a septic system or a municipal drain is an act of extraordinary waste. Here is the number that should stop you cold. A household of 4 people generates between 50 and 80 gallons of greywater every single day, not per week, per day. Over a full year, that is between 18,000 and 30,000 gallons of water you already processed, already heated, already transported to your property, and then deliberately discarded. Your survival garden, depending on its size and your climate, needs somewhere between 5,000 and 15,000 gallons of irrigation water per growing season. The supply matches the demand almost perfectly. You are already producing the water your garden needs. You are just throwing it away before it gets there. What I'm going to show you today is how to build a living biological filter system that takes that greywater, every drop from your household, that is not toilet waste, and converts it into clean, plant-safe irrigation water using nothing but gravel, soil, plants, and the microbial ecosystem that will colonize your system within weeks of building it. No chemicals, no power, no moving parts beyond the water itself, moving downhill by gravity. A system that processes water continuously, that improves with age rather than degrading, and that in a mature state produces effluent clean enough to irrigate vegetables without serious concern. This technology has names depending on who is describing it and at what scale: constructed wetland, living machine, phytoremediation system, biofilter. The names vary, but the biology is identical across all of them. You are building a miniature ecosystem, a marsh in miniature, that does what natural wetlands have done for millions of years: accept contaminated water, run it through a layered biological and physical gauntlet, and release genuinely clean water on the other side. Natural wetlands are some of the most productive and effective water treatment systems on Earth. They process agricultural runoff, urban stormwater, and industrial contamination at scales no human-built treatment facility could match economically. You are applying that same principle at the scale of your backyard. Let's understand the mechanisms before we build, because a system you understand is a system you can repair, troubleshoot, and adapt when something unexpected happens. A system you follow by rote fails the first time the conditions change. Greywater contamination falls into 3 categories, and your living filter addresses all 3 simultaneously through different mechanisms operating in different zones of the system. The first category is physical contamination: suspended particles, food solids, hair skin cells, lint from laundry, fine sediment. These are the easiest to address and the first to be removed. Physical filtration happens in the entry zones of your system, where larger particles are mechanically trapped by gravel and coarse material before the water moves deeper. This layer protects the biological zones downstream from clogging and gives suspended solids time to settle and begin decomposing safely. The second category is chemical contamination: soaps, detergents, cleaning agents, residual nutrients from food preparation, surfactants, phosphorus, nitrogen compounds, dissolved organic carbon. This is where the biology does its most impressive work. In the root zone of your filter system, the rhizosphere, which is the thin layer of soil immediately surrounding active plant roots. There is a density of microbial life that makes the rest of the soil look sterile by comparison. Plant roots are chemically active structures. They exude specific compounds that attract specific microorganisms, essentially farming the microbial community around them to serve their nutritional needs. That microbial community, in return, processes and metabolizes an extraordinary range of chemical contaminants. Phosphorus from detergents is taken up directly by plant tissue and locked into biomass. Nitrogen compounds are processed by nitrifying bacteria into forms plants can use, then removed from the water permanently as they enter the plant. Dissolved organic compounds from soap and food residue are metabolized by heterotrophic bacteria as a carbon and energy source. They eat the contamination. The biology is doing what biology has always done, converting one organism's waste into another organism's resource. The third category is biological contamination. Bacteria, some pathogens, microbial communities from human skin and food preparation. Pathogen reduction in a living filter system happens through multiple simultaneous mechanisms. Physical filtration removes pathogen-carrying particles. Competition from the dense, healthy, diverse microbial community in the root zone actively suppresses pathogenic organisms. A crowded, thriving ecosystem has little room for pathogens that evolve to exploit depleted or disrupted environments. Time and distance through the system progressively reduce pathogen concentrations. UV exposure in any open surface water zones provides additional kill. And the changing chemical environment as water moves through different zones, different pH, different oxygen levels, different microbial communities, creates a series of hostile environments that few pathogens can survive intact from inlet to outlet. A properly designed and fully mature constructed wetland system achieves pathogen reductions documented in peer-reviewed literature at 99% or greater for fecal coliform bacteria, with biochemical oxygen demand reduced by 80 to 95%, suspended solids reduced by 80 to 90%, and total nitrogen reduced by 40 to 70%, depending on plant uptake rates and seasonal temperature. These numbers match secondary wastewater treatment. Municipal treatment plants achieve similar results using concrete tanks, chemical dosing, mechanical aeration, continuous energy inputs, trained operators around the clock, and infrastructure costs measured in the tens of millions of dollars. Your living filter achieves the same results with gravel, cattails, and bacteria. The mechanisms are identical, the inputs are not. Now let's build the system. It has 4 components that connect in sequence, each flowing into the next by gravity. The inlet settling zone, the main filter bed, the plant canopy layer integrated into the bed, and the outlet collection and distribution zone. Component 1. The inlet settling zone. This is the first structure your greywater encounters after leaving your household drains. Its purpose is entirely mechanical. It is not doing biological treatment, it is protecting the biological treatment downstream from being overwhelmed by raw physical contamination. The settling zone is a tank or pit that receives your raw greywater. Water enters, velocity drops immediately as the container volume expands, and the physics of fluid dynamics takes over. Particles denser than water sink to the bottom. Particles less dense than water, greases, oils, soap scum, float to the top. What remains in the middle column of water is clarified, not clean, but physically separated from most of its solid and floating contamination. This clarified water overflows through a baffle or a simple pipe positioned at mid-depth into your main filter bed. The baffle placement is critical, below the floating layer and above the settled solids, drawing only the clarified middle water into the next stage. For a household of 2 to 4 people generating 50 to 80 gallons of greywater daily, your settling tank needs a minimum volume of 100 gallons. Larger is better. Volume means residence time, and residence time is what allows settling to occur. A tank that is too small fills and empties before particles have time to sink. Plan for your peak load, not your average, the Sunday evening when all the laundry happens, everyone showers, and the kitchen runs hard simultaneously. Your tank needs to absorb that surge without overflowing raw grey water directly into the filter bed. Construction options depend on what you have available. Poured concrete or concrete block construction is the most durable long-term option. A buried IBC tote, those 275-gallon food-grade plastic containers that can be sourced second-hand relatively inexpensively, works excellently and provides more volume than most households need, which is never a problem. Large food-grade barrels work for smaller household applications. Whatever you use, line any non-watertight construction with pond liner and ensure the structure is fully buried or insulated against freezing in cold climates. A frozen settling tank in January is a system failure at the worst possible time. The inlet pipe enters near the top of the tank. Extend it downward inside the tank with a T-fitting so the incoming water discharges below the surface rather than splashing. Surface discharge disturbs the settled solids layer at the bottom and resuspends material you've already separated. The outlet to the filter bed draws from mid-depth as described. Install a clean-out access at the top. You will need to remove accumulated bottom sludge periodically. Monthly inspection. Quarterly removal is a reasonable maintenance schedule for most household loadings. The sludge is biologically active organic material and should be buried at least a foot deep rather than spread on the surface to complete its decomposition safely underground. Component 2. The main filter bed. This is the biological engine of your system, and the component where design precision matters most. You are building what engineers call a horizontal subsurface flow constructed wetland. Water enters at one end, flows horizontally through the filter media below the surface, and exits at the other end. Subsurface flow is critical. Surface flow creates open water that breeds mosquitoes, creates odor potential, and exposes partially treated water to human contact before the treatment process is complete. The bed must be longer than it is wide. The length-to-width ratio should be a minimum of 3:1, with 4 or 5:1 being better. Why? Because treatment performance is directly proportional to the time water spends in contact with the biological community, what engineers call hydraulic retention time. A long, narrow bed forces water to travel further before exiting, maximizing contact time with the root zone and its associated microbial community. A wide, short bed allows water to short-circuit, to find fast paths through the system that bypass the biological treatment zones. Design against short-circuiting at every decision point. For a household of 4 generating 60 gallons of grey water per day, a bed with 25 to 30 square feet of surface area and a depth of 24 to 30 inches is a functional starting specification. If you can build larger, do. Oversizing a constructed wetland costs you some excavation labor and some gravel. Undersizing it costs you treatment performance, and poor performance in a system handling household waste has consequences you do not want. Excavate the bed to your planned depth. Line it completely, walls and floor, with 4-5 mil EPDM pond liner or an equivalent quality waterproof membrane. The liner is non-negotiable. You are not trying to infiltrate grey water into the surrounding soil. You are trying to contain it, treat it, and then deliver it specifically and controllably to your garden. Uncontrolled grey water infiltration around your home's foundation or into your neighbor's property is not a survival skill. It is a problem. The liner prevents it. Fill the lined bed in layers from bottom to top. The bottom 8 to 10 inches is coarse gravel, 1 to 2 inches in diameter. This is your flow channel, the highly permeable zone that allows water to move horizontally through the bed without restriction. Think of it as the highway that carries water from inlet to outlet, while the biology above it does the work. Above that, 8 to 10 inches of medium gravel, 1/2 to 3/4 inch diameter, the transition zone, increasing surface area for microbial attachment while maintaining adequate permeability. The top 6 to 8 inches is a mixture of fine gravel, coarse sand, and finished compost. This is your rhizosphere zone, the planting layer, where roots will establish and where the most biologically active and effective treatment will occur as the system matures. Across the full width of the inlet end of the bed, install a perforated distribution pipe. This pipe receives water from the settling tank and distributes it evenly across the entire cross-section of the filter bed, rather than concentrating flow in one corner. Even distribution is the single most important operational factor in preventing short-circuiting. Spend time on this. Use enough perforation holes, space them evenly, confirm the flow distributes before you backfill the gravel over the pipe. At the outlet end, a collection pipe running the full width gathers treated water that has completed its journey through the bed. This pipe exits through the liner, through the bed wall, and delivers your treated effluent to your garden. On this outlet pipe, install an adjustable standpipe or a valve that allows you to control the effective water level inside the bed. You want the water table inside the bed sitting just below the top of the gravel layer. The planting zone should be moist but not submerged at the surface. Adjust this level seasonally as plant water uptake changes with temperature and growth stage. Component 3. The plant canopy. The plants are not decoration. They are not even primarily a bonus food source, though they are that too. They are functional components of the treatment system, and the wrong plants or sparse planting will measurably degrade your treatment performance. Cattails are your primary workhorse plant, and a selection that will serve you best in most climates. Their performance credentials in constructed wetland treatment systems are unmatched at the household scale. Their root systems are extraordinarily dense and biologically active, penetrating deep into the gravel layers and creating the massive root surface area that hosts your treatment microbiology. Their nutrient uptake rates are exceptional. They pull phosphorus and nitrogen from the water aggressively, removing contaminants by incorporating them permanently into plant biomass. They tolerate waterlogged anaerobic root conditions that would kill most plants. They colonize aggressively, filling available space rapidly and closing the canopy completely, which is exactly what you want. And every part of a cattail plant has survival value. Young spring shoots eaten like asparagus, summer pollen collected as a flower extender, fall seed heads used as insulation or fire tinder, starchy rhizomes harvested year-round for carbohydrate, leaves woven into mats, baskets, and thatch. A plant that cleans your water and provides food and materials simultaneously is not a compromise. It is good design. Bulrush is an equally effective treatment plant with similar performance characteristics and similar survival utility. Water iris provides excellent treatment performance with the additional benefit of spectacular biomass production that can be harvested as mulch material. Phragmites australis, common reed, achieves outstanding treatment results and has been the most studied constructed wetland plant in the scientific literature. But check your regional regulations before planting it intentionally, as it is classified as invasive in parts of North America and Australia. For your outlet zone, where water quality is highest, consider integrating water celery, watercress, or taro into the planting mix. These are edible plants that tolerate wet conditions, take up residual nutrients in the increasingly clean effluent as it approaches the outlet, and provide direct food production from what is essentially your water treatment infrastructure. Plant your bed densely from the beginning. Gaps in the canopy are gaps in root zone coverage, which are gaps in treatment capacity. The bed should look overcrowded at planting. Within one full growing season, it will look exactly right. Water the plants with clean water for the first 2 to 4 weeks until they are established before beginning to route greywater through the system. You are establishing root systems and microbial communities before loading them with contamination. Component 4. The outlet and garden delivery system. Treated effluent leaving your filter bed outlet flows directly into your garden irrigation infrastructure. Gravity-fed drip lines are ideal. The elevation difference between your filter bed outlet and your garden beds provides enough head pressure to run a simple drip system without any pump, any power, or any mechanical components that can fail. Run drip lines under mulch to the base of your plants, delivering treated water directly to the root zone and away from leaf surfaces, fruit, and any above-ground plant tissue that might contact the water before it completes its final stage of treatment in the soil. This subsurface delivery approach eliminates the residual pathogen risk from direct contact with partially treated water and simultaneously reduces evaporative loss. The water goes from your living filter directly into the soil around your plant roots without ever touching a surface where it could evaporate or make contact with harvestable plant parts. Now, the timeline of system maturation, because this is where most people who build these systems become impatient and make mistakes that cost them. A newly built living filter system is not a fully functional treatment system. It is a constructed environment waiting to be colonized by the organisms that will do the treatment work. The microbial community in your root zone does not arrive fully formed. It develops over time, seeded initially by the microorganisms present in the greywater itself and in the soil and compost of your planting mix, then growing and diversifying as conditions stabilize and the plant root systems develop. In the first month, your system is primarily providing physical filtration through the gravel layers. Chemical and biological treatment capacity is minimal. Do not use this effluent on edible plants. Irrigate established trees, shrubs, or ornamentals where the treatment gap represents minimal risk. By month 3, the microbial community is establishing and beginning to provide meaningful chemical treatment. Root systems are developing into the gravel layers and extending the rhizosphere zone. You can begin irrigating fruit trees and established perennial vegetables, delivered subsurface with reasonable confidence. By month 6, a well-planted and properly loaded system is approaching its full treatment performance. The root zone is dense, the microbial community is diverse and stable, and the treatment mechanisms are all operating simultaneously. This is when your system begins achieving the 80 to 95% contamination reduction numbers that the science documents. By the end of the first full year, you have a mature living filter. It will continue improving slowly for several more years as the biology deepens and diversifies. A 5-year-old constructed wetland outperforms a 6-month-old one significantly. Your system gets better the longer you run it, which is the opposite of most mechanical systems, which degrade over time. A few critical operating rules that will determine whether your system thrives or slowly dies. Do not put toilet waste into this system. Ever. I said this before, and it bears saying again because the consequences of ignoring it are serious. Blackwater pathogen loading exceeds what a household-scale constructed wetland can reliably treat. Keep your greywater and blackwater streams completely separate. This is not difficult if you are building new. It is a plumbing design decision made once. If you are retrofitting, it requires some replumbing, but it is not complex work. Minimize bleach and strong disinfectants entering the system. Your living filter works because of microorganisms. Bleach kills microorganisms. A small incidental amount of bleach from occasional cleaning will not destroy your system. The biology is resilient and the dilution factor is substantial. A regular heavy load of bleach, cleaning the bathroom with bleach every week and running all that drainage through your filter, will progressively sterilize your root zone, and you will watch treatment performance decline without understanding why. Switch to biodegradable, plant-compatible cleaning products across your household. Soap nuts, Castile soap, citric acid-based cleaners, vinegar. They clean effectively, they biodegrade rapidly in your filter system, and in a true survival context, they are producible from local or storable materials in a way that bleach is not. Manage your loading rate. A constructed wetland has a treatment capacity based on its surface area and the maturity of its biological community. Exceeding that capacity, putting more contamination through the system than the biology can process, results in breakthrough, partially treated water exiting the outlet. Roughly 1.5 to 2 gallons of greywater per square foot of bed surface area per day is a workable loading rate for a mature system in a temperate climate. Below that rate, your system is comfortable and performing well. Significantly above it, performance degrades. Size your bed with a margin of safety. Inspect the system monthly. Check the settling tank solids level. Check that the distribution pipe at the inlet is flowing evenly across the full bed width. Check the water level inside the bed through an inspection port in the gravel surface. Check the outlet flow rate and quality. It should be clear to slightly tinted, without significant odor, and visibly cleaner than what went in. If something looks wrong, investigate before it becomes a larger problem. These are simple visual inspections that take 15 minutes. In winter climates, protect the biological community from freezing. A frozen filter bed is a dead filter bed, and recovery takes months. Mulch the surface of the bed heavily. 8 to 12 inches of straw or wood chips over the planting zone. The biological activity in the root zone generates some heat, and the mulch layer traps it. The water flowing through the system also carries some thermal energy that helps maintain temperature. In most temperate climates, a well-insulated bed will continue operating through mild winters. In genuinely extreme cold, you may need to divert greywater to temporary storage during the coldest months and resume loading in early spring when the biology reactivates. Here is the full picture of what you have built when all 4 components are operational and the biology has matured. Your household generates greywater continuously. That water flows by gravity into a settling tank that removes physical contamination before anything else happens. Clarified water flows from the settling tank into a horizontal filter bed, where a dense community of plants, roots, bacteria, fungi, protozoa, and invertebrates processes the remaining contamination across a distance of many feet and a residence time of multiple days. Treated water emerges from the outlet and flows by gravity to your garden, delivered subsurface to plant roots under mulch, with essentially zero evaporative loss and essentially zero residual pathogen risk at point of delivery. The entire system runs on gravity. It requires no electricity, no pumps, no chemical inputs, no consumable filter media that needs replacing. Its operating cost after construction is the 15 minutes per month of inspection and the occasional settling tank cleanout. It improves with time rather than degrading, and it converts what was previously a waste stream into the primary irrigation supply for a productive food garden. This is closed-loop water management at the household scale. It is what every self-sufficient homestead should have, and almost none do, because the municipal system made it unnecessary, and we confused unnecessary with unimportant. The municipal system is not permanent. The infrastructure that makes it work, the treatment plants, the pipe networks, the pumping stations, the chemical supply chains, the energy inputs, all of it is vulnerable in ways that have become harder to ignore. A living biological filter is not a backup plan. It is infrastructure that works regardless of what the municipal system is doing, because it does not depend on the municipal system at all. Build it before you need it. Commission it while conditions are stable so the biology matures before you are depending on it fully. And then run it every day, quietly, invisibly, turning the water you use back into the water your garden needs. Because the water was never gone, you were just not catching it.